So in the last session, we have discussed on the derivation of the velocity, acceleration, and we had solved a numerical to find the displacement, velocity, and acceleration in a simple harmonic motion. Okay. So today we will discuss about a spring mass system, which is also same as a, which is also exhibit simple harmonic motion. Okay. So you know this is this. Then let me say I have a I have a I have a spring. Okay. So I have a mass. And so let us say this spring is of stiffness K. Okay. So what is actually stiffness? So let us say this mass is at equilibrium position. This mass is at equilibrium position now. Okay. So let us say this mass is M. Okay. This is called a spring mass system. The mass is hanging by a spring, let us say from the top of the roof or whatever. Okay. So you just apply some a little bit of force there. Okay. You assume that there is no air resistance. You just apply a little bit of force. I mean, you just disturb it. If you disturb it, what will happen? This mass will get disturbed. It will come till this point. Let us say. Okay. It will come till this point. This mass. Uh, this mass will come till this point. Then it will try to go back to its original position. Then once it reaches the original position, it will try to overshoot. It will overshoot that. It will overshoot that original position. It will overshoot that original position. And this motion goes on like this motion goes on like it will go down like this. It will go up like this. It will go till this. Again, it will come back. Again, it will come back. So this is a ideal case when there is no air resistance. When there is no air resistance, this will this will keep oscillating. The mass will keep oscillating. Okay. So that is also a example of simple harmonic motion. Because that is also a simple harmonic motion because we have told uh, when about a mean position a point is moving like this. If it is moving like this about a mean position, at some point of time it will be here, at some point of time it will be here, at some point of time it will be here. It moves like this on a horizontal line or on a straight line, a vertical line. So this type of motion is also a simple harmonic motion, and it is the simple harmonic motion equation, as you know, is x is equal to x is equal to a cos omega t plus r. So this motion of this mass, which is hanging on a spring, is also an example of simple harmonic motion. Okay. So so now you know as per Newton's law, force is equal to mass into acceleration. Okay, mass into acceleration, and we know mass acceleration. What we have done? Acceleration is nothing but omega square into x. Right? That what we have studied. Minus omega square x or whatever, like minus omega square x. Right? We have studied velocity is equal to minus omega x. Acceleration is equal to minus omega square x. Okay. So you replace that omega square x in the force is equal to ma. you replace it as m omega square x. So this force is nothing but your restoring force. In a spring, when you try to displace it, there will be restoring force. Restoring force means it will try to restore it to the original position. That is called restoring force. Okay, so m omega square x. So this again, as per spring law, so this is one equation for force. Another equation for force is as per spring is F is equal to minus kx. That is another expression. Okay. Why? Because k is your stiffness. Okay. Means what happens like the displacement. So if this is, what do you mean by stiffness? If the spring is very stiff, if the spring is made of a very strong material, it is very stiff, then if you apply a force, it will get displaced by a lesser value. If it is very weak spring, then if you apply a force, it will get displaced by a higher value. So stiffness meaning is nothing but force per unit displacement. That means if for lesser displacement you are applying more force, I mean if F is more and X is less, then your stiffness is more. Right? So for a stiff spring, for high force will cause less displacement. For a less stiff spring, less force will cause high displacement. Yeah, so you are telling you are a stiff member. So if you apply force, it will get displaced very little. A strong member, a stiff member. So if you apply force, it will get displaced by very little amount. But if it is if for lesser force, the displacement is high. That means the stiffness of the spring is less. Okay. So you remember what is stiffness? Stiffness is force per unit displacement. So you are applying some force here, some force you have applied. That force it has caused some displacement. Let us say it has moved. Let us say this center line to this center line, this center line, this center line, and you have applied some force. So for force F, it has got displaced by x. So F by x is equal to that is the stiffness. Okay. So and if F is equal to minus kx. Why? Because when the displacement is going down, force will try to restore it. So force and displacement are in opposite direction. That's why you have to put a negative sign. So F is equal to minus m omega square x. That is one equation. Another equation of F is equal to minus kx. Okay. So then let us say this is equation 1. Let us say this is equation 2. So minus kx is equal to minus m omega square x. Okay. So OXX cancels, minus minus cancels. So omega square is equal to k by m. Okay. So omega is equal to square root k by m. So omega is nothing but your angular velocity or angular frequency, which is equal to stiffness by mass square root. Okay, this is very, very important. Okay. There can be n number of numericals which can be formulated based on the this equation. Okay. Knowing the mass, knowing the stiffness of the spring, you can find out what is the angular frequency, omega, angular velocity of the system. Okay. And again, you know omega. So 2 pi by t is equal to omega, you know. Because omega is angular velocity. So in a time period t, it covers 2 pi, right? In time period t, it covers 2 pi. So instead of so omega is k by m, or 2 pi by t
equal to
no 2 pi by t is equal to k by n square root, right? Then time period is equal to, you take t that side, okay? Then it will become 2 pi n by k. This will come this side.
yes.
So time period is equal to 2 pi m by k. Then frequency is nothing but inverse of your time period, right? So it will become 1 by 2 pi k by n. Just reverse.
Yes.
So these two equations, this time period and frequency are very, very important expressions based on which there can be n number of numericals which can be formulated. Time period is equal to 2 pi m by k. Frequency is equal to 1 by 2 pi k by m. So these are the equations you should always remember. Like for solving any number of numericals, these two equations will always be required. Okay. So that is one. Okay. They, so they will take an example of a spring mass system. Okay. So there can be like there can be n number of numericals where these springs can be in series, these springs can be in parallel. So one spring like this, another spring like this. So this is a spring in series. Okay.
Yes.
So spring in series, if you have studied electricity, the equivalent spring stiffness will be, it will be like a resistance in parallel.
It will be more.
Spring in series formula will be similar to resistance in parallel.
Yes.
And spring in parallel. What is spring in parallel? So this, let us say this is the system. So you have a spring like this, you have another spring like this. Then you are connecting it and you are putting the mass. So here the spring is in parallel. The spring in parallel is equivalent to resistance in series. So let us say the stiffness of this spring is K1, this spring is K2. In electricity, resistance in series is equal to R equal to R1 plus R2. Here springs are in parallel. So here spring equivalent is K1 plus K2. Okay. So a series spring or a parallel spring, you have to find out the time period and frequency. First, you have to find the equivalent stiffness.
Yes.
Once you find the equivalent stiffness, then only you can use it for finding the time period and frequency. Okay, there can be other arrangements also, like let us say like you have two springs in parallel like this,
Which is in
then another spring in series like this. So first you have to solve this and make it one spring, then these two springs will be in series. Okay. So the resistance in series is R1 plus R2, and resistance in parallel is nothing but 1 by R equal to 1 by R1 plus 1 by R2. So if you know this equation, you can find out the equivalent resistance. Similarly, spring in series is nothing but 1 by K, 1 by K1 plus 1 by K2. Okay. So we in our days we used to do the electricity, the resistance series, which was easier to derive. Okay. So after that we draw the similarity between this resistance in series equivalent to springs in parallel. Resistance in parallel is equivalent to springs in series. So that way we used to remember, and to find out the time period and frequency, first you have to derive the equivalent stiffness. Okay. So uh, time period is equal to 2 by m by k. So yeah. So they have. So you can take a picture of this. So here they are telling. We'll solve one example where the spring is in. We'll solve one example where the springs are in parallel. Okay. We will solve one example where the springs are in parallel. We'll solve one example where the springs are in parallel. So this one numerical you have like where you have a system, you have a system. Okay. So you so you let's say you have a spring and you have a mass and then you have another spring. Okay. So this spring is oscillating between this and this. Okay, so you just what you do, you just displace this thing by a little bit of force. By a little bit of force, you just displace this spring. So what will happen? On this when this is getting displaced, there will be inward force on the spring to bring it back to the original position. Okay. So similarly, like there will be another force to bring it to the original position. Okay, so force exerted by the spring on the left side trying to pull the mass towards the mean. Force exerted by the spring on the right side trying to push the mass towards the mean. So on the left side there is a force which is trying to bring the bring the bring trying to push the mass towards the mean. So this is the force exerted which is trying to bring the mass. So this mass is displaced, it will try to bring the mass this side. Similarly, when it is like this, there is another force exerted on this which will try to bring the mass in. So because there are two forces acting at the same time, the effective force on it is minus 2kx. Minus 2kx. Okay. So, so F is equal to Kx is this. So this is K, you can write as K equivalent. Okay. So K equivalent minus K equivalent. So K equivalent has become 2K here for this kind of a spring mass system. Okay, here it is nothing but springs in parallel. The springs in parallel is same as resistors in series. So resistors in series is R1 plus R2, R equivalent. Okay. Similarly, spring equivalent stiffness is nothing but your K1 plus K2. Here both springs have similar stiffness, so K plus K is equal to 2K. So here this kind of arrangement is nothing but springs are in parallel in this case. Just remember this is like springs in parallel. Okay.
Yes.
So your equivalent stiffness is 2K here. Okay. So your we have to find out the time period and the frequency. So we should always remember this time period is equal to
2 pi by
hmm. So we just know omega is equal to K by M. So omega is equal to K by M. Time period is equal to 2 pi by
omega is equal to 2 pi by
omega is equal to 2 pi by T. Because in time T it is covering 2 pi, right?
yes.
So to omega is equal to 2 pi by T. So
2 pi by t is equal to root k.
so 2 pi by T is equal to K by M. So so time period is equal to 2 pi M by K and frequency is equal to 1 by 2 pi K by M. So these two always remember. We have the tendency to mix up which is M by K, which is K by M. So just remember time period is equal to 2 pi M by K. So
Frequency
something
is
like
reciprocal.
reciprocal. So Tm, something like you remember this. Tm means for time period the numerical will be n,
Mass
the
will be
numerator
m.
will be m. So Tm, it will like that. If you remember, also it will be okay. So time period is equal to 2 pi m by k. Because you will get confused whether k by m or m by k. So Tm, if you remember like that as a shortcut, okay. Time period is equal to 2 pi m by k. So time for time period, at least you remember that it is 2 pi will be the this thing, not 1 by 2 pi. But anyway, if you get confused, you can always
Equate both of them.
equate and see where from it got derived. Like f is equal to kx is another one equation. Like and f is equal to ma is another equation. So m into k square, m into that is omega square x. Acceleration is nothing but your omega square x. So by equating these two also, if you forget by chance, you know my acceleration is omega square x.
Yes.
From here it is getting divided. So you know f is equal to kx minus kx.
That
F
is
is
also
equal to minus m omega square x. So if by chance you forget, you can derive from this past tense. But better to remember, t is 2 pi m by k. T for t, it is not 1 by 2 pi, it is 2 pi. Hmm. So this is the equivalent spring mass system. Okay. So in this case, the equivalent it's springs in parallel and equivalent stiffness is 2K. Okay. So there can be n number of arrangement in your worksheet. There can be n number of problem on this. So a spring there can be two spring. There can be, they will ask what is the equivalent stiffness and what is the time period, what is the stiffness for this kind of a system, or springs can be in parallel. So the springs can be in parallel. So the springs can be in parallel, and so this is a parallel spring, this is a series spring. How to find out the equivalent stiffness of those system, and then finally calculate the time period and frequency of the spring mass system. Okay. So this is very important. Okay. Hmm. Okay, so we are almost done with the spring. Remember that there can be n number of numerical forms found based on this. So this sometimes it is difficult to remember the equivalent stiffness of spring. That's why you remember like a spring is same as parallel spring is same as series resistance, and parallel series spring is same as parallel resistance. So this resistance was much easier because in electricity you have studied. Okay,
Current
this is my
splits in voltage.
so this is my resistor. Okay, so this is my resistor. This is the voltage, and this is the current flowing like this, and this is your voltage.
Yes.
So this is plus and this is minus. Okay. So here the current is the principle for this kind of parallel arrangement of resistors R1 or R2 is like the total current entering in is equal to total current entering out. Okay.
Yes.
So I in is equal to I out.
Yes.
So the resistance, the resistor where the resistance is more, it will draw less current. Yes. The resistor in which resistance is less will draw more current. Okay. So
more
that means
resistance, less current.
see, suppose the resistance here is 10 ohm, the resistance here is 5 ohm. So the if you are sending some 3 ampere current,
more current
then
will go to
the
5.
5 ohm will take 2 ampere current and 10 ohm will take 1 ampere current.
Yes.
So that is how for a parallel resistance system. Similarly, for series resistance, it is very simple. So it is these two resistors are in series. This is your voltage, and this current is always flows from positive to negative. You know, electron flows from negative to positive. Current flows from positive to negative. So this current is flowing. So the here the driving principle is the current remains same throughout the circuit in resistance in series. current remains same, but difference is the total voltage is equal to voltage drop across these two
the two resistors.
resistors. So here you write it as V is equal to I into R equivalent. Okay.
Yes.
And again V is equal to voltage drop across resistance R1 plus voltage drop across resistance R2. Okay.
Yes.
So voltage drop across R1 is nothing but your I remains same. Okay. I into R1 plus I into R2.
I
Right?
into R1 plus R.
So it becomes I R is equal to I R equivalent is equal to I into R1 plus R2. So you got R equivalent derivation. R equivalent is equal to R1 plus R2. So similarly, you can show me like you derive the equivalent resistance for resistance in parallel. So you can draw a similarity between resistance and
your voltage will be constant.
Yeah.
Your current is constant.
Yeah, in series, current is constant.
Your voltage.
Total voltage or the battery, whatever it is, it has some voltage. So the total voltage is equal to sum of voltage drops.
Here
Okay.
you equate.
Here I. So I into R1 plus I into R2 is equal to I into R. That is the driving equation. Yes. Whereas here
you have to equate for current.
Yes.
V by R1 plus V by.
No, not current actually. So here the total voltage drop. Total current remains same.
Yeah.
Sorry. Current in is equal to current out. Okay. So that you can the total voltage drop across this and across this are same. Total voltage drop across this and across this are same. Uh, so that is the voltage remains same across both the resistor in parallel. Yes. Okay. Whereas the current get divided.
Current splits in.
Current splits. So you this is homework for you. You show me how to derive the equivalent resistance for a for resistance in parallel. Okay. Series is very simple. The current remains same. The total voltage is equal to voltage drop across resistance R1 plus voltage drop across resistance R2. So IR equivalent is equal to IR1 plus IR2. The driving thing is that here I and I1, I2, everything is equal. I is equal to I1 is equal to I2. So that's why IR1, IR2, you are not writing I1 R1 or I2 R2 because all I are same. That's why you are simply you are able to derive the equivalent resistance when the resistance in series. Yes. For parallel, you derive it and show me. Okay. Then after this, we'll solve something related to energy in simple harmonic motion. That half kx square, how do we derive? And we will do some then we'll touch upon in the simple pendulum. Okay, how to derive the time period of a simple pendulum, what you do in your laboratory. Okay. So there it will be time period equal to 2 pi. So here you are saying a time period m by t by equal to 2 pi m by k. So that m will get replaced by L there. So 2 pi L by G. L by G. So if your pendulum is of length L and it is doing a simple harmonic motion, your pendulum, so the time period will be 2 pi L by G. Okay. L by G. Just remember this that in place of M, it will be replaced by L. Instead of K, it will be G. So there can be problem on spring, there can be problem on simple pendulum. So in simple pendulum, they will give the length of the pendulum. Okay. So here in this equation, you have to replace 2 pi m by k in pendulum 2 pi L by G. So once you know time period, you can find the frequency. So it is because yours are MCQ questions, you have to write down these formulas and by heart these formulas to do things faster. Yes. Clear? So we'll do this pendulum derivation and solve some numerical example and some energy principle in spring, half kx square and all, how it is being derived, we'll do in the next session. Yes. Okay. Thank you. You solve the equivalent resistance for resistance
That.
in parallel. Okay.